And we're back. Okay, so continuing on with some important properties of the student t-distribution. So the t-distribution is different for different sample sizes, and that'll have to do with basically the width due to the variability of those different distributions. Now, the t-distribution also has the same general symmetric bell shape as the standard normal distribution, but it reflects the greater variability, so the different widths, as expected with small samples. And the t-distribution also has a mean of t equals 0, but the trick is the standard deviation of the t-distribution differs depending on sample size. And the standard deviation of the t-distribution varies, again, with sample size, and when it is greater than 1. Now, as the sample size n gets larger, the t-distribution gets closer to the normal distribution. So here's a visual where you can see, alright, so this orange shape right here, that's that bell shape for a t-distribution with sample size n equals 3. And the red one is a t bell-shaped distribution with sample size n equals 12. And then the blue is supposed to be the standard normal distribution. So notice as we went from 3 to 12 that the t-distribution now got closer to the standard normal distribution, and it shows how the t-distribution and the normal distribution are related, because in essence, as your sample size increases indefinitely, then the t-distribution would become the standard normal distribution, essentially. Now, there's a couple other things you can still do with any of these confidence intervals where we estimate the means. You can still find the point estimate mu, or essentially that sample mean. If, say, you're given just a confidence interval, you could still do that upper limit plus lower limit divided by 2. So just taking the mean, you'll figure out what that sample mean is. Or you can still find the margin of error by just taking that upper limit, subtracting the lower limit, dividing that by 2, just like we did in the previous section, which of course you can rewatch those videos if you feel you want a refresher on those. Now, we can still find what sample size will be best for whatever mid-conference intervals we will be looking for. And just, let's see, a few little things to keep in mind. So we're still using mu as our population mean, sigma as our population standard deviation, x bar as a sample mean, s will be the sample standard deviation, e is the margin of error. And when we're finding sample size, we're going to be using z critical values each time. And same idea as before, if we want to find the sample size, we usually want to round up into our next whole number. Even if we get something like 0.01, we want to keep rounding up each time, because it's always better to have more samples than fewer. Now, something to keep in mind for when we want to find the sample size when that population standard deviation is not known, we need to estimate the population standard deviation somehow from whatever sample we're given. So ways we can do that are still using the range rule of thumb. So if we have some values from a sample, we can just find that range, then divide it by 4. And since that's what the range rule of thumb allows us to do, that'll help us estimate a sample standard deviation, which is what we use instead. And we can start the sample collection process without knowing that population standard deviation. And using the first several values, and we can calculate the sample standard deviation and use it in place of the population standard deviation. So the more estimated value of the population standard deviation can then be improved as more sample data are obtained, and the sample size can be refined accordingly. So essentially we can estimate it with a sample. And we can also estimate the value of the population standard deviation by using the results from some earlier study. So essentially just kind of using some intuition if we really need to, but being able to actually calculate a sample standard deviation will be best, or using the range rule of thumb. So here's an example going through one way we could find the sample size. So assume that we want to estimate the mean IQ score for a population of statistics students. how many statistics students must be randomly selected for IQ tests if we want 95% confidence that the sample mean is within 3 IQ points of the population mean. So when it's saying within 3 IQ points, that's our margin of error, essentially. And we still, when we're trying to find sample size, like we did in the previous section, we still are essentially basing everything off the margin of error, and what we want that to be. So we're using 3 as our margin of error here. Since we're dealing with a 95% confidence, we're using 1.96 from the z table as that critical value, which is the z value that would give us that middle 95% between positive 1.96 and negative 1.96 for z scores. Then let's see, the alpha values, so those are just kind of knowing what we have from before, but we don't necessarily need them to plug into that formula to find the sample size. And so using this standard deviation of 15, it's kind of going based on assumptions and from previous problems in the textbook that we didn't get to go over, but we'll go ahead and use the 15 and just know that for standard deviation, again, we would want it to try and find a sample standard deviation from a few sample values or use the range rule of thumb. Those will be better for when we're trying to find the sample size when we don't know the population standard deviation. Again, we're just kind of going to plug everything into here, but I want to just walk through the algebra of how we can find the sample size first. So again, start with margin of error equal to that critical value times the standard error, which is just the standard deviation divided by square root of sample size. So one thing you can do here to start solving this algebraically is just multiply both sides by the square root of n. I'll take it out of the denominator on this side and leave it times e over here. And then divide that margin of error e on both sides. So you'd have the square root of n equal to the critical value times the standard deviation, all divided by the margin of error. Then, just to get rid of the square root, we just have to square both sides, which we square in all these values here. So essentially, we can use this as a little formula for finding sample size, or a desired sample size, for a confidence interval used to estimate population means. Where it's just n equals that critical value squared times the standard deviation squared, all divided by the margin of error squared. So then I can just plug in those numbers into that formula for this particular problem. So just using that 1.96 as a critical value for 95% confidence, 15 for that standard deviation, both of those are squared and multiplied together, and then all divided by that margin of error 3 squared. That would come out to 96.04, but again, we always want to round up, so we're going to use 97 as the desired sample size for this particular example. Now, with a simple random sample of only 97 statistics students, we'll be 95% confident that the sample mean is within 3 IQ points of the true population mean mu. It can be a little interpretation of the sample size we found there. So now part 2 of this is where we cover ideas more in chapter 7-3, which these are essentially the same ideas as in the previous section, finding a confidence interval to estimate the population mean. Just this time we're assuming that we actually know the population standard deviation, which may not always be the case, hence why I want to go over 7-4 first, but we could use these ideas as well if we did know the population standard deviation ahead of time. And let's see, they're still just kind of dealing with some of the same notations here. Just this time, again, we'll know that population standard deviation, and when we do know it, we're going to be using z critical values instead of t critical values, which is just kind of the main difference, really. When you don't know it, use t. When you do know that population standard deviation, use z. And again, these are just a few of the same requirements here for when we want to find that confidence interval. We want to deal with simple random samples. This time we'll want to know what the population standard deviation is, and then we'll want to have a normally distributed population, or just make sure that we have a sample size bigger than 30. Now, plugging everything in for the formula is just about the same, just this time our margin of error, again, is just using a z critical value instead. Then times that standard error, we've got the population standard deviation, then still divided by our square root of n. And you can use either that inequality notation or this parentheses notation. Both are totally fine. So here's one possible example that's a little morbid, which seems to be strangely common in statistics problems for some weird reason. But here we go. People have died in boat and aircraft accidents because an obsolete estimate of the mean weight of men was used. In recent decades, the mean weight of men has increased considerably, so we need to update our estimate of that mean so that boats, aircraft, elevators, and other such devices do not become dangerously overloaded. But using the weights of men from a random sample, we obtain these sample statistics for the simple random sample. From 40 men, we get their mean weight was 172.55 pounds. And from there, research from several other sources suggests that the population of weights of men has a standard deviation given by standard deviation equal to 26 pounds. So that's the population standard deviation essentially based on past studies. So just continuing on with this example, we're going to find the best point estimate for the mean weight of all men, construct that 95% confidence interval. Then from there, we want to see what the results suggest about the mean weight of men, 166.3 pounds. That was used to determine the safe passenger capacity of the water vessels in 1960, as given in the National Transportation and Safety Board Safety Recommendation, M-04-04. So essentially, we're just going to talk about if that 166.3 was a good thing to be used based on our interval we're going to find. So part A, just again, a sample mean is the best point estimate for a population mean. So we're just going to use that 172.55 pounds. For that 95% confidence interval, so I'm just going to plug everything in. We know alpha is 0.05. So alpha over 2 is at 0.025. If we need a refresher there. Then we're just going to use that 1.96 for the critical value for the 95% confidence interval. Plug everything in to find our margin of error. So 1.96, 26 is that population standard deviation, and all divided by our square root of 40 for that sample size. And so our margin of error comes out to about 8.057. Then we just kind of plug everything in to figure out what our actual confidence interval is. So which looks like our confidence interval lies between 164.49 and 180.61 pounds, that is. Now based on the confidence interval, just basically seeing if that 166.3 was good. So however, the best point estimate of 172.55 pounds suggests that the mean weight of men is now considerably greater than 166.3 pounds. So considering that an underestimate of the mean weight of men can result in lives lost through overloaded boats and aircrafts, these results strongly suggest that additional data should be collected. And so at least this 166.3 pounds would technically fit inside that confidence interval, but this is just a little logical reasoning thing here. We would want to overestimate rather than underestimate, which is always best. So in a problem like this, you could argue that the 166.3 should be fine since it's in the confidence interval, but you could also just argue that it just doesn't seem right, so you'd be safer off overestimating. And here's just a little chart to kind of help like visually see when you should use which distribution, the t distribution or the z distribution, and whenever we're using confidence intervals. And ultimately, it kind of comes down to if you know the population standard deviation or not. If you don't, if you do know it, and depending on whether or not these conditions are satisfied, you're going to be using the z distribution. If it's not a normally distributed population and you don't have a sample size bigger than 30, there are other methods you can use for finding a confidence interval, but we won't be getting into those during this class, at least not until later. And if you don't know the population standard deviation, you can go through this and basically you'll just be using the t distribution anytime you don't know the population standard deviation. Most time, z will be used for confidence intervals on proportions, and t will be used for confidence intervals on means, just depending on whether or not we know the population standard deviation. Just kind of summarize it again here, and that's it.